Hello students, in this video I will be talking about concepts related to interests compounded with a frequency of n. So this title actually sounds a little abstract. Let's get to an actual problem where perhaps it will make a little more sense. So in the previous video I went over TJ Bank offering 2% annual interest compounded annually. And the deposit for a deposit of $1,000 after 5 years, it will grow to $1,104. So let's say now I have Metro Bank, okay, offering 2% annual interest, compounded monthly. How would the savings of $1,000 differ in 5 years? So it sounds rather enticing, okay? So what does it mean to compound monthly in this case? So to compound monthly implies that we are going to, the account will appreciate in a monthly basis. That's what it means. Remember, what it means to compound is we are going to grow, right? We're going to grow at a monthly basis at a rate of 2% annual, okay? So how does that translate? So interest rate is 2% per year, but the frequency of compounding is monthly. Growth will happen at 12 intervals, at 12 equal increments. So what this really means is, okay, at the end of each month, the percentage, okay, or the interest that you're going to collect will be 1/12 of 2%. So let's try to map this out on a chart like we did in the previous video. So at the very beginning, okay, beginning of the year, we will have $1,000 at Metro Bank. By the end of the first year, what will happen is we will have collected 1,000 times. Remember, this is going to be our new rate, right? I'm still going by this formula. So the new rate at the end of each month is 1/12 of 0.02. And how many times will I be collecting in a year? It will be 12 times per year. That's why it's being raised to the 12th. Well, what will happen after the second year then? In the second year, right, the same kind of the same stuff will go into the set of parentheses again. However, I'm changing my time now. So how many times will the account have grown? It will have grown 24 times in 2 years. And then in the third year, and then in the fourth year, and finally in the fifth year. So by the end of the fifth year, compounding monthly, okay, the account will have grown by more than $1, which actually sounds very gimmicky, doesn't it? But in actuality, okay, when an account is compounded more frequently, you are going to, at the end, come out ahead. You will come out ahead. And let's say if a bank has millions of customers, okay, across the country, then what this dollar difference will translate to is millions of dollars that they're going to have to fork over, right? So, you know, for an individual account, it may not necessarily seem like it's a lot, but if we're talking about the grand scheme of things, okay, having it be compounded more frequently is actually against the bank's interest, which is why in most cases when you go to a bank and ask for a savings account, they'll never, I haven't come across a bank where they will offer you an interest rate compounded more frequently than annual, okay? So most banks will only offer interest compounded annually. Well, that's because this is the least amount of growth. Okay. So how can we try to take the situation here and all of these things that that are listed out. How can we maybe transcribe this into another working formula? Because it does feel like we're doing something slightly different from applying p times 1 plus r to the t, doesn't it? So how can we modify this? Well, the modification will look like this. So the formula where the frequency of compounding is different from the unit of time in the rate of growth or decay can be modeled by this situation now. So before, where we had p times 1 plus r to the t, right, and r was the interest rate, let's say it was like some percent per year, then this t happens to also be in the unit of years. If you look at this now, 12 times 2, 12 times 3, 12 times 4, what is that? These are, so this would be 24, is it years? It's actually months, right? And this is 36 months, and then this is 48 months, and so forth, okay? We're still evaluating things in years. However, by putting this 12 in the front there, we are now converting the unit of time from years to months. This percentage, okay, which was 2% annual, if I multiply it by 1/12, it's become a percentage, a monthly percentage rate then. Okay, so what we're really doing here, okay, is, again, we're compounding monthly, okay? What that translates to is we're the account will be growing at a monthly rate, and because of that, okay, the account will at the end grow a little, slightly quicker, okay, than an account that's compounded annually. Anyway, we'll go through more examples where this will be a little more prevalent, but you know, I started off in the last video with a real world problem, and I thought I would continue in this video with a real world problem. But let's take a look at another scenario now. Alright, so the value of land in a particular city appreciates at 10% annual, compounded quarterly. If nothing changes for 10 years, what is the value of a $1 million property in 10 years? So why does the land appreciate? Why is it compounded quarterly? This actually has to do with when the value of land is assessed, right? So when in New York City, actually, they issue quarterly statements about, you know, how much your land has appreciated or depreciated. Whenever those things are issued, okay, that causes more hype, and more hype causes greater appreciation, and greater appreciation, well, that means the situation, okay, will be compounded, okay. Anyway, I'm not saying that that is an exact scenario, but it has a lot of influence, and there's actually more complex models, okay, of things like this. What we're doing here, we're just playing around with basic exponential equations. But let's take a look at how we can apply the last formula to talk about this situation here. Okay, so $1 million property, right? Appreciating at 10% per year, so that's 0.1 per year. N will equal to 4 because there are 4 quarters in a year. So at the end of every quarter, the value of the property will grow, which means I will need to convert this 10% into a quarterly rate. The initial value is $1 million. So if I make the appropriate substitution into this equation, right, I have $1 million times 1 plus 0.1 over 4 to the 4t. What am I going to substitute in for t? I'm going to substitute in 5. Okay? So what this translates to is roughly close to $2.7 million, okay, in 10 years. which actually kind of sounds about right. The rate of inflation and the value of property appreciating, looking at New York City, that does, sound rather close, okay, to reality. Well, what if the appreciation was compounded annually? Okay, so like I said before, because the assessment comes out quarterly, okay, that causes more hype and uh, in the market. Okay, so let's say if the assessments came out annually, okay, and that would cause maybe perhaps a decrease in hype. Okay, so what if the situation here was compounded annually, meaning we're only going to see growth happen once a year. Okay, so still at 10% annual, how would that affect the value of the property in 10 years? Well, again, I'm dealing with the situation very, very similar, but this time the frequency of compounding is the same as the unit of time in our interest rate here. It's 10% annual. Okay, that's the unit of time. It's per year, and I am compounding per year. So if I substitute in these values for 10 years, what I will end up with is roughly $2.6 million. So, as you can see here, by increasing the frequency of compounding, this will actually cause an increase in the final value. And this is actually no surprise because when an account grows, okay, and you observe that growth, and then another period of time passes, and then you observe the growth again. If you increase the frequency of that, okay, you will see this compounded over time and grow even faster and grow even more. Let's look at another situation where where we see this kind of phenomena happen again. Alright, so suppose a new smartphone valued at $1,000 was purchased. Once purchased, it depreciates at 40% per year, compounded annually. If the same phone remains unpurchased, meaning like in the store, no one buys it, okay, the phone will still depreciate at 40%, however, 40% per year, however, it's going to be compounded monthly. So let's say, the latest iPhone, okay, or Samsung phone or whatever, okay, and there was an overstock of that particular product, and it stays in the store for a long period of time. Of course, that value of the phone will depreciate, okay? However, it's going to depreciate, but it's going to be compounded monthly. Let's take a look at the values of the phones in these two situations here. What is the value of the phone 5 years after purchase? Okay, so 5 years after purchase, okay, what that would mean is, okay, and it's compounded annually, right, because it says compounded annual. So the model says that my initial is 1,000, R is depreciating, so it's negative 0.4, T is 5 years. So if I make the appropriate substitution, I'll end up with this as my value. So it ends up being $77 in 5 years, which sounds about right. I mean, like if you're carrying a phone that you spent a ton of money on, okay, 5 years ago, at present, because it's been used, and the overall value of the phone just depreciates because new technology comes out. Yeah, it's $77. All right, what happens if if there was an overstock of that device in the left in the store? Well, in 5 years, if left in the store, if I make the appropriate substitution and compound it monthly, okay, I'll end up with 1,000 times that expression there, that depreciation divided by 12, and the depreciation, okay, is going to be compounded 12 times a year, or 60 times over 5 years. The value of the phone will be higher than when it has been used, which sounds about right. If you buy a brand new old iPhone, okay, probably that's going to be about the price that you're going to be spending on there. Which again, this is another example where it shows where if you compound the if you increase the compound the frequency of compounding, the value of, you know, said thing will be higher at the end. Okay? All right. So here is the summary of all the formulas that we've covered thus far. Again, the difference, okay, between these two formulas really just rests in the frequency of compounding, okay? So the idea is we're taking the percent growth or percent decay per, you know, unit of time, and we're subdividing it even further. And we're increasing the number of times that the object is going to grow or decay. As a result of doing so, the overall value or the overall end result is going to end up being higher than if we were to compound at a smaller frequency.